Hello, universe. Here we go. Run a simulation and play with expected values. Nope. I do have.
That's what I wanted to know.
Oh, have I showed you guys my loaded dice yet? Oh, I forgot to bring those out. I just blew it too. I shouldn't have told you.
Oh.
You roll a 6-sided dice 10 times. Do and record it.
0 for me.
What?
Oh, roll 8. Got it. Never mind. I thought you meant roll a number 6.
Oh, you didn't get it?
Out of
Roll
10.
a 6-sided
I got a
dice.
6 on 6 trial.
Oh, that's cool. A 6 on a 6 trial. Very nice. So, let's bring up the spreadsheet too. Oh, who's that? Minerva. Hello.
Yeah.
Can you hear me? Hi.
Yeah.
Excellent. All right. Oh, I forgot to share my screen. Crap. I hate when I do that. All right. Now you should be able to see stuff. And anyone looking at this in the future, this will make more sense. Here's what we're doing. So let's whip out. Oh, you know what I could do is the random dice thing. Random dice roller. I like random.org. And we're going to roll 10 of them. Bang. Okay, so there are mine. 5, 1, 3, 6, 4, 1. I can just steal that image. Let's do that. Okay, so here's mine. Yours probably look a little bit different. We rolled 10 times, right? So on average, what number did you roll? Like, let's suppose I was going to give you $1 for every dot you see, for the dotted kind. Let's see, what would I have done? It was $1 for each of these. So we've got 5. Yeah. So imagine a game where you get $1 for matching the number that you rolled. So 1 is $1, 2 is $2, 3 is $3, and so on. Then I would have just won $31 here. On average, out of 10 rolls, I rolled about a 3 on average. What did you guys roll on average? Curious.
4. But my sum was 33.
Your sum was 33?
But
If you
I
divide
rolled
by, how many times did you roll?
10 times.
Oh, so 33 divided by 10 would be 3.3.
Yeah.
Right.
But
Okay.
and I rolled 4 3 times.
You rolled a 4 3 times. That was you rolled more 4s than anything else. So 3.3. Anybody else have an average they got?
2.6.
2.6. 5.5. Whoa. 5.5. You rolled a lot of 5s and 6s, huh? Oh my gosh. Kelly, did you get yours yet? Okay. Did
But
you
yours-
add up
Add it all up.
and divide by how many? And divide by 10? Do you have any dice rolling there, Minerva?
Yeah, I got 4 times 4. So 10 times that I rolled a 4.
Your average is 4? What if you
Yeah.
add them all up and divide by 10? What do you get?
Um, 0.4.
Yeah, 4.8. No, it should be somewhere between 1 and 6. So for example, on mine, I added 5 plus 1 plus 3, 6, 4. All these added up to 31. And I divided that by 10 to get 3.1.
Okay.
Hold on, I need to take this back. I rolled 3 times.
Oh, that'll throw it off a little bit. All right, Christian's messing with our data here. Okay, so 5.5 is a mistake.
So mine is 3.8.
Okay, that sounds good.
Four.
So it's a 4.3.
4 and 4.3. Okay. So, so as far as what you expect to happen with this game, do these seem like reasonable averages?
Yeah.
Like the 5.5, did that seem like, I was a little like shocked at that one, but it's possible.
Yeah.
I mean, you could roll 10 sixes, that's totally possible. That's the best you could do. Worst you could do is roll 10 ones, that's possible too. So the average has to be somewhere between 1 on the low end and 6 on the high end. Would you agree with that? Roll 10 sixes, 60 divided by 10 is 6 on average. So this average value goes by another name in probability. It's also called expected value. And we were doing it playing around experimentally. We're going to do it theoretically in just a moment. So let's see if I go back a page. I just want to break down this data in a slightly different way. I'm going to make a table. So I could have rolled a 1, a 2, a 3, a 4, a 5, or a 6. I rolled a few 1s. Right? There's 1, there's another. I rolled 3 1s. Did I roll any 2s? No, I rolled a couple of 2s. Did I roll any 3s? I got 1 3. Did I roll any 4s? It looks like I have 1. I also got a 5 and 2 6s. So this would be another way to summarize my data. This is called a frequency table. And it's the same data that you see right here. It's just broken down a little bit different. A table like this allows me to do what's called a weighted average. Okay, so I'm just going to show you a weighted average in case you haven't seen that before. I bet you have. It's just been a while. 2 1 1 1 2. Okay. That would be. There we go. So weighted average. So I could have gotten, let's suppose I rolled 6 times. And I got a 1, and then I got a 2, and then I got a 3, and then I got a 4. That. And then I got a 5, and then I got a 6. Right, that's one possible thing that could happen with 6 rolls. Now I rolled 10 times, and that's not what happened. I found that I got 3 1s. I'm going to put a little times 3 in there. And I got 2 2s. And I got, let's see, 1 3. And I got 1 4. And I got 1 5. And I got 2 6s. So the black numbers here are the weights. Because I got more 1s than anything else. So it gets a higher weight. So all the weighted average is how many times did each of the things occur? And if you add up the black numbers only, what will the black numbers add to? The 10 trials that I did, right? 3 plus 2 plus 1 plus 1 plus 1 plus 2, that should add up to 10. Okay, so the weights always have to add up to the total amount of occurrences that happen. So a weighted average is you just write each of the elements that happen, and then you divide by how many things happen, like 10 things happen here. So let's just double check what my weighted average comes out to. If I clean up the arithmetic here, 3 ones is 3, 2 twos is 4, 1 3, 1 4, 1 5, and 2 sixes.
So that knocks out everything you don't have.
If you didn't roll something, you would have a 0 by it, or it just wouldn't be present in the list. And so then I keep cleaning this up further. So what do I have? 7, 10, 14, 19, and 12. Oops, that's supposed to be
I was
10.
gonna say, where'd the 12 come
I have
from?
no idea. Over there. I don't know. So I got a 31 out of 10, which is exactly what I found before. I just added them up a different way. There's my 3.1 average that I had before. So that's a weighted average.
Same.
And so weighted averages, as soon as kids start learning about averages, either that year or the next year, they start seeing weighted averages come up. So you probably saw weighted averages, maybe 6th grade, middle school math, if you think way back. I have no recollection of it, but I'm sure I saw them somewhere back there. I'm just used to them now. So what I'm going to do is I'm going to put another twist on weighted averages, giving what we know about probability. So let's suppose that this is all the data I have, and I don't quite understand. I think this is a fair dice, but I really don't know. But I'm just going with these 10 data samples. So according to my data, the probability of rolling a 1 is 3/10, according to my data, right? That's what my experimental data shows. The probability of rolling a 4, what would that be, according to my data? It's a 1/10 chance of rolling a 4. Okay. Now, the law of large numbers says you got to roll a lot of times to get the theoretical probability. Is 10 a lot? For my 9-year-old, yeah. For me, no, it's not a lot. It doesn't fit in the law of large numbers. But let's just make believe it does for now. So here's the slight twist we're going to take on the weighted average. Gotcha. The probability for me of getting a 1 was 3 out of 10. So to get a 1, I had a 3/10 chance of doing so. And then I have a possibility of getting a 2. The probability, according to my data, was 2/10. Right? The chance, according to what I've seen, is 2/10. The chance of getting a 3, according to my data, I believe that was 1/10. The chance of getting a 4, that was also 1/10. The chance of getting a 5 was 1/10 for me. Let's see if I can drag it and make a little tiny bit more space. And the chance of getting a 6 was 2/10, according to my data. So what I'm curious about is, what if I take the value of the outcome, that's that 1 there, times its probability? Now, if you think about that for a second, compare this statement right here to the weighted average. So there's the weighted average. There's my new probabilistic version of it. Are they the same statement or a different statement, do you think?
Same.
Yeah, they're really the same, right? Because
They add up to 10.
3/10, how do you add fractions?
You add the top numbers. as
And,
long as
and,
it's
and you have a
numbers.
common denominator, right? So really, the denominator here, every one of these is a 10. So according to the way I add fractions, I can rewrite that sum from direction this way. When we write it this way, we call it a weighted average. When we write it that way, there we go, we call it expected value. It's the same idea. compute this sum product thing, I'm gonna get 3.1 again. So we have 3 different ways to compute this average. The first way we called it an average. The second way we called it a weighted average. The third way we call it expected value. Expected value is a powerful idea in statistics and probability, and so that's what we're going to explore for the next half an hour, 45 minutes. Expected value. So expected value definition is, this is going to blow your minds, the value of what I expect to happen. That sounds kind of crazy, doesn't it? Value of what I expect to happen. And mine again came up to 3.1. Probably should add a little disclaimer to this. When I roll a 6-sided die, am I going to always get 1s? No. Am I going to always get 6s? No. If I do it enough times, I should expect to get about as many 1s as 2s, as 3s, as 4s, as 5s, as 6s. Right? So let's suppose I had an ideal thing happen, and that when I rolled, I got a 1, and then I got a 2, and then I got a 3, and then I got a 4, and then I got a 5, and then I got a 6. It could happen. What's the average of these 6 numbers? What number is right in the middle? Because they're in order and equally spaced.
3.5.
Yeah, 3.5 is the number in the middle. Because they're an arithmetic sequence, the number in the middle falls exactly between the 2 middle numbers because there's an even number of numbers. We saw that back in 211. So the average value is 3.1 and 3.5. And if we look back at our list of averages, what do these guys kind of sort of hover around?
3.
3 to 4. 3 to 4, yeah. If we add these up and divide by 1, 2, 3, 4, 5, 6, 7, then we'll have the average of rolling 70 dice. So let's whip that out real quick. Get your favorite arithmometer out. Whip out my Google arithmometer. Excuse me for just a second. Get that sheet right back. There you go. .64. Add them up. So I added them up. They got 25.5 if I type them right. Divided by 7 gives me a 3.64. So, you know, the law of large numbers, we now have 70 rolls instead of 10 rolls. We're closer to 3.5 than any one of us really was. So 3.5 is the theoretical. So make a note, average of 70 rolls was about 3.64.
I got 4.25.
When you added these up and divided by 7?
Yeah.
1, 2, 3, 4, 5, 6, 7. You did something wrong.
3.1 plus 3.2 plus 2.6 plus add them all up.
See? Did you divide by 7 in the same shot or something?
Exactly.
Okay. So that's the experimental expected value. The theoretical expected value is, there you go, right here. So the average of the outcomes, because these are all equally likely, that's important. There is a 1/6 chance of getting a 1, and there is a 1/6 chance of getting a 2, and there is a 1/6 chance of getting a 3, and a 1/6 chance of getting a backwards there. Okay? And a 1/6 chance of getting a 5, and a 1/6 chance of getting a 6. So when I clean this up, this is going to be 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. And they all have a common denominator, right? So isn't that the same as what we did up here? Just a different way of thinking about it? And that's going to be that 3.5 in the end. So that's the theoretical average, which is called expected value. So if we roll a 6-sided dice a ton of times and add them all up, we expect to get, on average, a 3.5. Somewhere between a 3 and a 4, which is right in the middle. If this was a game we were playing, and we get $1 for a 1, and $2 for a 2, and $3 for a 3, and we played this game 1,000,000 times, on average, we would have won $3.5 per trial, per roll, or $3.5 million. Now, did you ever have a game where people just paid you for playing it and you didn't have to pay to get in on it? Doesn't usually work that way, does it? You usually have to pay to get in on the game somehow. Right? Games of chance, right? So here's the question for you. How much would you be willing to pay to play this game?
Maximum?
Yeah.
2 or 3.
I don't play max bet, I play pennies.
50 cents.
We can do pennies instead of dollars, right? If it makes you feel better. But that, so think about that for a second. Write something down. How much would you willing to pay this game? Then we're going to run a little math on it and see if that's a reasonable thing to pay.
Let's put, fair game.
Yes, this is like, is it a fair game? Exactly, yeah. We're going to see if we can come up with an amount to pay and see if it's fair or not. Okay, Kelly?
50 cents.
Okay, so we have some different ones. Christian said $2 or $3.
Are we talking about?
So playing the game is you roll the dice once.
Okay.
How much would you pay to win? I would have won $3 there, but what would I pay to get up? Christian said $2 or $3.
That's usually what we should be able to pay, because the person that has you roll the dice, they think, well, if they roll a 2 or 1, I want some profit.
Yes, but if they get a 5 or a 6, then I owe them money.
If it's a 4, 5, or 6, the
Yeah.
person
So
rolls.
now it just sounds like a game of craps.
It's, yeah, well, we're looking at a simple game of craps, exactly. Yeah. Kelly said 50 cents, so $0.5.
I'm with
Everyone else?
Kelly.
You're with Kelly, you pay 50 cents for it?
Minimum bet.
Minimum. That's the most you pay, you mean?
Yeah,
You wouldn't want to pay more than that.
no.
So I'm going to pick the $2 one because that's kind of a middle ground. So I want to analyze the situation for what happens with $2, right? So I'm going to make a new table out of this. And so in the table is going to be the outcome of the roll and then your profit. Profit at 2 F's, that doesn't look right.
1.
1 F. Put that off there. It's amazing. I can remember all this math, but profit, certain words, you just can't do it.
1,000.
1,000.
100 versus 1.
Oh yeah, I can't get the zeros right. Okay. So let's say we're gonna pay to play $2. So if I roll a 1, I paid $2, but I got 1 back. So overall, I would have lost $1 to play that time. Does that make sense? If I roll a 2, then it's a break even. I paid 2, I got my 2 back. If I roll a 3, I paid 2, they give me 3 back, I'm 1 ahead. See the pattern? 4, I would make a $2 profit. 5, I would make a $3 profit. And 6, I would make a $4 profit. So now I don't care about the roll so much anymore. What I care about is this value right here, that value column. That's what matters to me now, because that's what I'm making. Because a 1 is worth negative $1, 2 is worth $0, a 3 is worth $1 to me in the end. That's what matters. Next, what's the probability of this scenario right here, of making negative $1? What's the probability that's going to happen?
6.
It's 1 out of 6. What's the probability we break even? 1 out of 6. Probability we make $1?
Same one.
Okay, so again, they're all 1 out of 6. So what I'd like you to do for me now is calculate the average value of this scenario. So just like we calculated the value of getting a 1, 2, 3, 4, 5, or 6, what's the average value of negative 1, 0, 1, 2, 3, and 4? Whip something out. What is the expected value here?
If you were to roll 6 times.
You could roll 1,000,000 times. This is theoretical. We're not doing the experimental version. We could play that in a minute. Oops. Down. Right, expected. We got a number?
Yeah, I have a number on what's right though.
What do you get?
I got 9.
So there's 2 ways we can do this one. We can multiply each money outcome by its probability, or since they're equally weighted, we could add up the number column and divide by 6, because they're equal. I got 1.5 when I did that. Anyone else get that? No, I didn't get that. All right, help me out here. I could have totally made that up.
I got 1.5.
You got 1.5? Okay, I got one person on my side.
Yeah.
This 9.5 because the profit was $9.06.
That's what I have as my number 6.
Okay, so you add those up to the 9, you divide by 6, and you get,
Yeah.
which is excellent. Yes, okay, so we're finally coming on the same page here. Yeah, so
Oh, got it.
you got it now?
Yeah,
Okay, so this is 3 over 2 or 1.
I just didn't take it far enough.
So what does that mean again? So what that means is if you paid $2, so in the long run, you play this game a lot. You would win $1.50 per trial. Theoretical uses the law of large numbers to compare back to experimental. Experimental is anything we physically do, like go to a gambling house and gamble. Right, so make believe we're at Gary's gambling house and this is a game you can play. Is this good for my house? This game?
No.
No, I'm losing money on it because you're walking away with $1.50 per try.
But that's after you paid $2.
Yeah, your profit. So if you played this 10 times,
You get your additional investment.
you would have 10 times, you get your initial investment back, plus you still make 1.5 on average. This is your profit, not your revenue. So if you played this 10 times, on average, you would expect to walk away with $15 you didn't have when you came in. That's what this is telling. That make sense?
Yes.
Okay. Kelly? No, you
No,
would
you're
win.
making.
This says, because it's positive, you would win. Okay, let's redo it. So Gary's thinking, oh, this is bringing people in, but I'm losing money left and right. I'm not gonna be able to stay in business. So I come up with a similar game. And this time you pay $4. Yes, Kelly?
How many times you,
How many times do you play? As many times as you want. You can pay 100 times if you want.
it was $2 and played 10 times. Paid $20.
You would end up paying $20, correct? But you would win more than that. According to this, although you would have paid $20, you would have won, let's see, if you played 10 times, you won $1.50 extra each time, right? Because remember our table back here? Our table takes into account what you paid. You won $1, but you paid $2, so overall you lost $1. So we're doing profit, not revenue here. So we're gonna keep that in mind. All right, so let's do the $4 version. Roll versus profit. What's the profit if you win $1
-3.
and you lose 3? Here you lose 2, lose 1, break even. Gain $1, gain $2. So what I want to know is for this column right here, what is the expected value? Sometimes they call it E. Our book does that. E for expected value. -0.5, yes, that's what you should get. That's what I got too. So the expected value here you should find is -50 cents. And there's 2 ways we can do that. Because they're equally likely, we could add them up and divide by 6. If they're not equally likely, then you have to do it the long way. -3 times 1/6 plus -2 times 1/6. And you keep multiplying the outcome times its probability. That's the technical way to do expected value, which is a weighted average. In here, so what does this -50 cents mean then in English? Like, I want to explain this to my mom, who's a big gambler, right? Just kidding. Oh, sorry. It means what?
So you paid $4 per trial and there's 6 trials, so that's
Well, no, here,
$24.
this is theoretical. This isn't saying I've done 6 trials. There are 6 possible outcomes. I could have played this 10 times, 1,000 times, or only twice.
Got it, okay.
Experimental. That's a whole nother issue. This is a theoretical answer. Kind of like the probability of getting a 1 is 1/6. That's theoretical. My data didn't show that when I rolled 10 times.
Okay.
So what does this mean? Because this is theoretical.
Did you just use each time you played?
It means that on average, if you play a bunch of times, you lose 50 cents each time. Even if you got 6s a bunch of times and 1, 2, came back with $2 extra, if you play it enough, you'll end up a loser overall. So if you play this 100 times, 100 times 50 cents is $50.
But you're putting in $2 each time.
No,
Or you're putting in
$4.
$4. This takes into account that. Right? We've already accounted for that in this column. So that's irrelevant now. So you paid $4 every single time you paid.
Sometimes Christian, you would get money, you would win. Yeah, so that's
Yeah.
where this is a lot.
Sometimes you would get it too. But the bottom line is if you played this game 100 times, what I would expect to happen is you would end up being $50 in the hole. You would have lost $50 overall. Whereas the other game we played where you pay $2, you made $150 each time. So if you played this game 100 times, I would expect you to, on average, my customers would walk away with $150 in their pocket they didn't have before. That's what this is telling us.
More expensive because
So sort of, yeah, the more expensive it is, the more you're going to lose overall. So is this version of the game fair? Not to me, the owner of the house. You're overjoyed. Yeah, I'm making money on average. Okay, not fair. Is this version of the game fair? No, it's not.
Fair to you, but not to us.
It's not necessarily fair to me. I'm making a profit. It's not fair to you. So fair means it's fair to both sides. So what would it have to be fair on both sides? Let's try $3. Okay, that's another suggestion.
Just rock, paper, scissors it.
So new page.
That one was 50 cents more than the first one was off, but now these going.
Somewhere in between. Okay, let's check it out. Let's pay $3 and see what happens. Do the calculation on paying $3. Make your table. Roll versus profit. What do you think, Christian?
Christian's just gonna be working
No. Danielle?
57.
50 cents, yes. The expected value here is 50 cents. So you play my game 100 times. On average, you make 50 cents each time. So you're going to walk away with 50 bucks of my money. Not fair, I cry. I want my money back. To be fair, the expected value should be 0. So that's what fair means in this context. We both agree it's fair. So fair for us means the expected value would have to be 0. So that's the question. What could it be to be 0? Let's see, $3, you make money, 50 cents on average per try. $4, not fair to you, I make 50 cents every time you play. 3.5 maybe is the magic number. Okay, let's test that out. Kelly, what were you gonna say? 2.5? Yeah, we tested, so far we've tested $2, $4, then $3.
We said
And-
3.5?
And we're starting to think 350 is the magic
Because
number.
4 gave us a negative 50 cents.
And 3 gave us a positive 50
So I'd
cents.
say split the difference.
Put it in the middle, yeah, it should work out. So let's see, that should work. Roll versus profits. 1, 2, 3, 5, and 6. Let's see, I would be down, ooh, whoa, that was crazy. And it's out of control. I would be down 250, right? Here I would be down 150. Here I would be down 50 cents. Here I would be up 50 cents. Here I would be up 150. All 50, and here I would be up 250, right? And if you look at adding this list of numbers up, and again, we can add them because they're equally weighted, the positives and negatives cancel each other out. And so I get a sum of 0 here. 0 divided by 6 gives us an expected value of 0. Finally, we have a fair game. Okay, so here's an interesting thing. Magic button. Go, guys. There you are. Why 350? Why was that the magic number to make this fair? Yeah, the numbers on the dice are 1 through 6, and the average value of 1 through 6 is 3.5, and it turns out that's the amount to pay to make it fair.
Isn't there a game where roll 2 dice, and because the numbers on opposite sides of the dice equal 7, you have to get those 2 opposites rolled to get 7. And where your odds are balanced on getting 7.
Sounds like craps, right?
Yeah,
Wasn't that
kind of
right?
sounds like craps in a sense.
Yeah.
That's why they have all the little extra rules in the crowds.
Yeah. You can have a hard number, you can have a soft number. You can,
Game at the beginning of Eldorado.
Oh, really? Okay. So this is expected value. So we take some game and there's an outcome. In this case, we're saying profit is the outcome. And basically what we're asking here is what is the average profit? And that just depends on the particular game. We finally set up a game where the average profit was 0, so that means it's fair for both sides. So that's expected value. So, Kelly?
It really actually moves up.
Yeah, so what they do is gambling institutions try to make the expected value just a little tiny bit on their side. So they make money, but enough people win that they keep coming back. So they would want to set the expected value from your point of view to something like maybe negative 0.1. So on average, they make 10 cents per person, but some people walk away with a good amount.
So does that explain, like, when you go to play penny slots,
Yeah.
you think penny, I'm only going to bet 1 penny, but their their minimum bet is actually 50 cents.
Yeah.
Is that because that's the weighted average, the expected?
No, so those games are much more complicated than this because there's a lot of different ways the penny slots can come out. And nowadays, they used to use mechanical algorithms to make that happen. Now they use mathematical programming. And it's not this simple, but it's the same idea.
Got it, okay.
Yeah. So, like, for example, I used to work at a dog track when I was trying to get my way through college, and they would post the odds on the board. So you talk about what odds. And what they would do is they would weight the odds slightly. So let's say we knew a dog won half of its races. Now, if they made it an equal wager, you pay 50, you win 50, they're not going to make any money. So what they do is they tilt it just a little bit in their favor, so that they make a little money off a lot of people. Some people make money enough to keep coming back to them. So they want to make it enough so that they make a profit off you, a marginal one, not a huge one, but enough people win so they become an offer. That's the way it works. We're a society that's into gambling. There's very few societies that don't gamble, which is fascinating. Something weird about our brain. All right, so let's take a look at odds next, because that'll help us with that gambling aspect. And then what we're going to do is we're going to look up the Powerball and check out the expected value of Powerball. See what that's like. So odds. There's two kinds of odds. There's odds against and odds in favor. And just like probability is a fraction, odds is a fraction also. So odds against is unfavorable outcomes divided by favorable outcomes. Guess what odds in favor are going to be? Yeah, what fraction? So this is the fraction that tells me what odds against are. Unfavorable over favorable.
1 to 1, 1 over.
I don't know.
No, what's the description of odds in favor? It's going to be favorable outcomes over unfavorable.
Oh, I see. I
Generally.
guess I do try to ask favorable over.
And so I'll give a couple of examples to illustrate. So let's go back to the dice for a minute, and let's say I'm going to make up a new game and you only win when you roll a 2. On the 6-sided dice. What's the probability of rolling a 2? 1 out of 6. There's one favorable way that can happen. There are 2. There's 6 possible ways that can happen. Right? That's probability. Favorable outcomes over total. So the odds against the 2, so odds against, yeah, would be all of the unfavorable outcomes. Well, those are all the other numbers I could get, and there's 5 of these. And there's one favorable outcome. So it'd be 5 out of 1 for odds against. Yeah, 5 to 1. There's 5 to 1 odds. So for this to be a fair game, I would have to pay you, or you would have to win $5 for every $1 you wager. We'll check that out, see if it works. Odds in favor would be one favorable way, 5 total ways it can happen, or 5 ways it can't happen, excuse me. Odds versus probability. When we're talking about odds, if you add up the 2 numbers, that gives you total possible outcomes. So let's check this out. So I'm going to use the odds against to come up with a fair game. View page. So we're going to still do the roll A2 to win. $5. Profit. Otherwise, you lose $1. Yeah, so you can think of it, it's $1 a play. If you roll a 2, you get $6. Your net gain is $5. Okay. So you could walk out of this game with $5. Okay. What's the chance that's going to happen? 1 out of 6 chance that's going to happen. You could, on the other hand, walk out of this game losing $1. Okay. What's the chance that's going to happen? So we're calculating the expected value. We're taking the outcome times the probability. All right, so if I clean this up, much simpler version of before, 5 times 1/6 is 5/6. The other fraction is going to be a negative 5/6. So what's the expected value here? 2. So is this a fair game? So if you played this particular game 1,000,000 times, on average, you would expect to win $0 per try. Sometimes you win $5. More often you lost $1. It balances out in the long run. Could you have a run of 100 tries where you're making a ton of money? Absolutely could. If you keep playing, you will lose that. That's what the law of large numbers says here. So we're comparing theoretical, this is all theoretical, to experimental, if we play this a whole bunch of times. All right, so we can use odds to make a fair game, which is kind of cool. So if I were a gambling institution, I would not want to make those the odds, because that would mean I don't make any money off you. So I would want to do something different. I might want to do something like have your profit be just a little bit less. So instead, maybe I would say your profit is going to be $4.90. But you could lose $1. And so if I redo this, that would be the 490, which happens 1/6 of the time, and the -1, which happens 5/6 of the time. Overall here, I should find that we end up with what? Negative 0.1 out of 6. Zero point 016-ish. The calculator help me out on that. That's about right. Yeah. So this is from your perspective, not my perspective, the gambling house. It's from the player's perspective. So on average, I can say that's approximately 2 cents around. So you're going to lose 2 cents per play. If enough, that means I'm going to win. The house is going to get 2 cents every time somebody plays. Some people walk away with money, but on average, if enough people play this, I'll make 2 cents per person per play. So if 1 million people played my game each week, let's see, what would I end up with? 100,000. I'd end up with $20,000 if 1 million people played each week. Times 2 cents. It's not bad. I can get 1 million people to play. Online, yeah, online that can happen, I'm sure, pretty easy. So that's the idea of expected value. You take the value of the outcome and you multiply it by its probability. So often you'll see notation X is some outcome. And when we're calculating expected value, we take the value of X, whatever it happens to be, and we multiply by the probability of X happening. And if we add up all of those possibilities, that's what we call expected value. So we sum the value times its probability, and that's it. Sometimes you'll see the E written with a little parentheses X, where X is the possible outcomes. So for our previous example, when you had a profit of $5 or a loss of $1, X was either 5 or negative 1. When we were counting all the 6 numbers, X could have been 1, 2, 3, 4, 5, or 6. All right, let's look up, see if we can find some information on Powerball for expected value.
Actually does calculate what your odds are.
Powerball? Ooh, you want to share some numbers with us? What do you got? Let's see. Here's my screen. So what did you come up with?
Your odds of winning the Powerball and the Jack would be 1 in 26 billion 972 million 431,200 $200.
200. Okay.
Those are your odds for winning.
So these are odds in favor. How much can you win in this game, in Powerball? Like, what's the big jackpot going on?
The starting jackpot is 3 million exactly.
Okay. Starting
Goes on last Wednesday, so one time.
jackpot is 40 million. Okay. So we're going to use the odds in favor to come up with the expected value of playing Powerball. So the expected value here, and what's it cost to play? $1?
$2.
$2. Okay.
$3. Yeah, $2.
So pay $2. And that one's sloppy. Let me try it again. So let's see. We could lose $2. And as far as probability goes, how many different ways could I lose $2? Well, there's 26,972,431,200 ways that can happen. That's my numerator. 26,972,431,200. How many total things can happen? Well, that plus 1. So the total number of outcomes with Powerball would be 26,972,431,201. And I could win though. How much would I win? Well, heck, I would win $40 million. I think that's 40 million, isn't it?
Yep.
Yeah. Okay. And there is one possible way that can happen out of 26,972,400. I said that wrong. 972,431,201. Yeah, that's right. Let's see if we can make that calculation. Your favorite arithmometer. Let's see if we can get lucky here. Okay, so Google Calculator. I think I'll put this in a spreadsheet. And then we have to interpret what that means. That's the interesting part. There's a slight error in our calculation. It's funny in a minute. That's okay. It's close enough. All right, typing this into my spreadsheets. Let's see where those go. 6, 7, 2, 4, 3, 1. Over that plus 1 times, that's the probability. Probability of losing. Probability of winning is almost the same thing, but a 1 time. All right, so I'm going to show you my spreadsheet here. Let's see. So I typed my probability of losing here, which is that 26 billion, or roughly 26 billion. And Google says it's pretty close to 1. What's 1 mean as a percent? 100% chance. So Google's saying you got about 100% chance of losing. And the probability of winning, according to Google right now, that's about 0. Now I could ask Google for more decimal places, so let's do that here. Oh, there we go. Oh, finally I'm seeing some numbers in there. Okay. And, well, that's not the expected value. All I'm listing is probabilities. That's not what you got for probabilities?
Yeah, I got 0.00148.
Oh, something's wrong. It shouldn't be that. It should be much smaller. Okay, so as far as the expected value goes, then what I want to do is I want to take the amount I would win times the probability of winning and add that to the amount I would lose times the probability of losing and get an answer. And so that's negative 1.999. Now keep in mind, these guys right here, those are dollar amounts, which means that's essentially a dollar amount too. Now Google rounded it for me just now. And so let's see. Google's saying that on average, if I played this game a lot, I would expect to lose $2 per play. Oh, wait, interesting. What am I paying? $2. So if I played this game, you know, like 100 billion times, even if I won a couple of times, I would have lost a lot more And overall, I'd still not won enough to keep up with my losings. That's what this is showing me here.
So it's saying is it's not worth playing.
Oh no, it's not saying it's not worth playing, it's just the expected value is negative for you. So if you, in the long run, if you take everybody that's ever played and you added up what they paid in versus what got paid out, on average, the state made $2 per person.
That's like the capital lottery.
Yeah, and think about it though. The whole reason states do lotteries is to win, to make money. It's an income generator. So it's got to be at least a little bit in their favor. Here, it's $2 per play in their favor. With a $40 million jackpot. Well, let's up the jackpot, right? Like, well, let's pick a better jackpot. How about 80 million? Let's see if that changes things much. Shit, nothing changed. Okay, so let's see. 80 million versus, well, how many ways are there to lose again?
Over 26 billion.
26 billion. So that's almost 30 billion, right? Okay, so let's compare 30 billion to 80 million on a number line. Ready? Everyone draw a number line.
Or the numbers again?
I'll show, the numbers are 30 billion versus 80 million. So let's see if we can draw this. So I'm going to try here. So let's see, here's 0 on my number line. And then at the end of my number line, I'm going to put my 30 billion. Okay, so there's 30 billion. So now I got to figure out where the heck 80 million goes.
Close to 0.
Yeah, right. So if that's 30 billion, then 1 billion is going to be somewhere over here. And how many million are in a billion?
1 million.
No, not a million billion, not a million millions. How many millions are in a billion? How many places are there for that? There's 1,000 millions in a billion. Okay. So in the distance from here to here, I have to fit 1,000 millions. I only need the first 80 of them. All right. That'd be right about there, or now a little closer. Yeah, I can't even draw where it is actually. So given that there's almost 30 billion ways to lose, should I make a feasible jackpot in the millions? Really, I mean, I could try. I could make it like 800 million. I don't think that's ever happened. It ever will. But we could try.
What's that one?
Oh, was there?
You didn't hear about that?
I don't remember that one. So here's.
Wait, what was it?
The Powerball jackpot
Oh.
about a month ago. It got to 1.6 billion.
Okay, let's check out 1.6 billion. So that's twice what this is. This is 800
That was the
million.
highest one. That's right.
Okay, so that would be 1.6 billion. So there's millions, I think thousands, hundreds. Actually, I have no idea if I have enough zeros.
Use the
One, oh crap. Ones, thousands, million, billions. Okay, I did it. Oh yeah, 1.6 billion really changed the outcome of the state, didn't it? They went from $2 to $1.94. Isn't expected value? Is it kind of hard to wrap your mind around? But we got to think. Expected value means law of large numbers. That means this game needs to be played a lot of times. How many is a lot? Well, probably more than 30 billion for this number to make sense. But bottom line is, even though they're going to pay out a ton of money, they make way more.
So is that why they say like getting one ticket versus buying 1,000 tickets is not going to?
It doesn't make a difference. You can't buy enough tickets to make a difference.
Because if you buy enough tickets, why even
What
try?
would we have to do to make this a fair game?
lower the price.
So let's think about that for a minute. Let's try to make the lottery a fair game. This is going to be fun.
How can we tweak this?
We can tweak anything. All right, so let's see. Oops. A fair lottery. Everybody's looking. This is like fairy tale.
Fairy tale lottery.
Fairy tale lottery. All right, so let's see. We want to make this fair. So things that we're stuck with in this game are the probabilities. And the probabilities are 1 in, and just to make it simple, I'm just going to call it 30 billion because I can't keep track of all those spots. So 1 out of 30 billion. Is that right? I think that's what I was
Place every week.
What? Oh, I guess it doesn't matter which number I use, because the next probability is a total pain in the ass. But, excuse me. Because for the next one, if there's one way to win out of 30 billion, then there must be 29,999,000,000, blah, blah, blah. So the next probability is that, 29,999,999 ways to lose. And so we have to make, there's a couple of ways we can do this. We can have two different variables. So we have win versus lose here. Outcome and money. This is a win, that row, and this one is a lose. Okay, so let's make something simpler. Let's say that you only pay $1, so you could lose $1. Okay, what would you have to win for this to be true? Now, to be fair, so let's see. Remember odds against versus odds in favor? Didn't that help us make a fair game before, last time we did it? So what are the odds in favor here? They would be the ways you can win divided by the ways you could lose. Okay, so what number is the ways you can win? The 1, there's one way you can win. And the ways you can lose, well, that would be this guy right here. Here is the 1. This would have to be the winnings for it to be a fair game. You see it? Because then when we multiply across these, because that's the way expected value works, I multiply these two together, I multiply those two together, and then I add coming down. And that's expected value. So the only way this is going to be fair is if I make the 29,999,999,999, if that's the jackpot. That's the only way this is going to be fair. That will balance it. Because then when I multiply the top two numbers, I'll get 29 blah, blah, blah billion over 30 billion. Down here, I get -1 times the 29 billion over 30 billion. Then I have the positive version and the negative version of the fraction, add them up and I get 0. That's the only way to wash it out. Odds in favor and odds against help you make a game fair. So maybe we just want to be like, it's only slightly fair. And so then we would just drop it to 28 billion instead. Then the state would make a little bit of money. And we could double check that. My spreadsheet's set up to do that. So if I just check that, we're almost out of time. You gotta go, Kelly. We'll see you later. So let's see. What were our numbers before I lost them? Christian, it was what, 28?
26.
26. So let's say I made, let's forget about the millions, because a million versus a billion, that's kind of like pocket change, right?
It's 26.9.
Okay, so I'm just going to go with 26 billion, 1, 2, 3, 1, 2, 3, 1, 2, 3, is that right? That's right, yeah. So instead of 26 billion 900 million-ish, if we just made the jackpot 26 billion, the state is still going to make at least $1 per person. Because these are from your perspective, is what we've calculated, not the state's perspective. That means each person will, on average, over playing billions of times, lose $1 per try, even though they won sometimes. How much do they win? 26 billion. But you would have had to play so much to finally win that, you ended up losing one. Now that's impossible for any one individual to play that much, but over the whole population, it's possible to get rid of it. So two important aspects of probability: odds versus expected value versus probability. Now think about this. Earlier in the course, when we were flipping coins, or early in this unit, I said, what's the probability of getting ahead? Somebody said 50-50. Yeah, 50-50 isn't probability, it's odds, yeah. So people are used to talking about odds. It comes up a lot with gambling. So anytime you look up something about payoff, they're always showing odds for payoff. That's how they calculate it. They tweak the odds against, so the house ends up making a little money per person. But some people will make it big. But enough people lose, the house isn't big. Expected value helps us figure that out. And we've been pretty good at this for several hundred years, this calculation. People finally figure it out. And I think we're done with stuff for Math 212. Woo! Okay. That's about the end of it. Let's see.
So Wednesday, we're doing our,
So Wednesday would be a good day to take the exit exam.
and we have two chances, right?
You get 2 tries on that. So I would try the practice one. If you need more practices, let me know. I can make up some more versions of that.
Can you go ahead and just do it? I want multiple practices.
Multiple, okay, I'll
Yeah.
make a note to put multiple on. Debbie asked that I put up an answer key for the final practice final, and I haven't done that yet. I need to do that ASAP. And Greg asked that I get the take-home final out today, so I will get that done. Let's say by tomorrow, I'll have that stuff done. So more exits, sample answers. What's the other thing? Take-home. Okay. Other things, if anybody wants to retake an exam, you can do that a week from today. And that grade will supersede your existing grade, so you must do better. It's optional. You don't have to do it. It's your call. So you'll need to let me know Monday next week. And then if you're in Hermiston, I can send it there. If you're in Pendleton, I would just expect to see you here. Otherwise, we can just have a review day if anyone needs more review next Monday. And this Wednesday is a review day. We're going to go over stuff the whole term. Okay. Questions?
Nope.
Minerva or Debbie?
I have a question for my exit exam. Can I do that the same day that I take the final?
Yes,
Or do
you
you?
can.
Okay.
That's fine.
Final just.
Greg, what was your question?
13, that's just this semester. Finals just this semester.
Yes, it's not covering 211. Yeah, the final is just what we covered this term.
Say, dang, I hope it's not next term too, or
Last term.
Last term.
Yeah. Yeah, it's just the chapters we covered this quarter.
Right, see you Wednesday.
All right.
So for next Monday, there won't be a recording. It'll just be anybody that wants to retake something, correct?
Yes, and if you have stuff you want to review, just call me up and I can do a live chat with you.
Okay.
Minerva, are you going to be here next Monday? Your mic's not on.
Yeah, I plan to be there.
Okay.
I have it arranged to be there.
Okay, excellent. And are you going to be here Wednesday or are you going to be there?
Depending on how long we go on Wednesday, I plan to go
To
on
Pendleton?
Wednesday.
Okay. All right. If something changes, just let me know.
I will.
All right. Anything else?
No.
All right. You guys have a fantastic day. I'll see you soon.
All right. Bye.
Bye.